Okay then, so how about we go ahead and look into a couple examples of how to calculate your moments. So in this instance here, we've got this lever here attached to the shaft at O. So the idea here is we're applying some sort of force at the end of this lever in order to cause rotation of that shaft. And in that instance, so first off, we're starting with a 100-pound force at the end of the shaft, at the end of the lever applied directly downwards, and we're going to be calculating the moment about O that causes. So first things first is to go ahead and draw a little free body diagram. Probably technically not completely necessary for this problem, but it's a good habit to get into at the very least. Help you down the road. So again, got our component there. We've got the dimensions labeled. We've got our force applied. So we're figuring out the moment about O. The moment about O. So the most foolproof way to go about doing that is essentially to go back to what the original definition of your moment is. The moment about a point is equal to the vector of the displacement from that point to the point of application of the force. So that's here, not here. Different directions will give you the wrong answer. So from the point you're measuring to the point of application, times crossed with the force that's being applied, the vector of the force that's being applied. So this displacement vector here, we can break that up into basically its unit vector components. So our I and J components. So that'll just be based upon the angle that this component here forms between the x and the y axis, times a magnitude and its units. So this basically the unit vector portion there tells you kind of what direction it's pointing. This tells you how long it is. Then we got our force vector. That one's fairly simple. It's it's a vertical force acting downwards. So that's just negative 100 pounds again in the J. So to be thorough, we can use this methodology here. So our I, J, K, and then just repeat the I and the J so we can do our determinant without having to cross these boundaries. So you follow you multiply out your I vector times the J component of the displacement vector times the K component of the force vector, and that ends up being 0 because there's no K component. Repeat that. It turns out that for this instance, there's only one thing that ends up being a non-zero number. So the moment, the R crossed with the RF ends up being 12 inches crossed with negative 100 pounds. And again, that's we keep the signs on that because essentially when we're doing our determinant here, we're going forward here. If it had been a different instance, if the values that had been left were this, then we would switch the signs. But so our moment vector ends up being either negative 1200 pound-inch or negative 100 pound-foot. So that's the moment for that scenario. Next thing that they want us to do is find out what sort of horizontal force would cause the same moment. So I just drew a quick sketch of that to orient ourselves. And we can do the same thing here, except we're replacing the we're throwing in a horizontal force here. So that'll go under our I, the I portions of the force, and then of course obviously the vertical force becomes 0, and the force in the Z direction remains 0. So we end up doing that. Turns out that the only remaining non-zero one is this one here. So again, that ends up with 20.8 inches crossed with our FH, but we throw the negative sign on there because we're slanting to the back when we're using this methodology rather than to the forward. So take that value, equate it to the value we previously found, and then just solve for FH, making sure that we're canceling out our units. So that's why I use the pound-inch one instead of the pound-foot one. Canceling out our units, our inches here cancel out, and we end up getting 57.7 pounds once we round to a reasonable number of significant digits. As for the next portion of the smallest force that you could apply at A, which would produce the same moment, well, we know that the moment is maximized when the force is applied directly perpendicular to the displacement vector. So, using my little pen here, when I'm applying the force right here, that's when the moment's at its maximum. Not when I'm doing this, not when I'm pushing like this, not when I'm doing this. It's when it's perpendicular, either this way or this way. That's when the magnitude is the maximum. Obviously, you still need to keep your sign conventions in mind. So essentially, we'll just equate those two. So we've got we know the value we're trying to match for the moment, and we know that from our graph that this vector here, that this distance here is 24 inches. And that'll give us the magnitude of our F min. So again, we could do this the long way and kind of figure out, do the individual, I and J components of the forces in question, and corresponding to corresponding to the I and J components of the force when it's acting at this angle. But again, I think that's a bit of overkill. We know what angle this is, so we've already got the vector. Even if we haven't necessarily solved for the unit vector, we know what it is, and we know what angle it's working at. All we need is the magnitude of it in order to give us enough information to define the force. So take that, solve for F min, ends up being 50 pounds. Next thing we're looking at, the location for a 240 pound vertical force to produce the same moment. Now, if we hearken back to the first question, we found out what the moment caused by 100-pound force is at this displacement here. So essentially, we know that, you know, if we're acting along, if we're simply moving the point of application of the force, then what we're changing about the r isn't the unit vector. The unit vector stays the same. All we're changing is the magnitude that we multiply it. All we're changing is the magnitude that we multiply it by in the front there. So essentially, if we know that we want these two things to be the same, then and the magnitude of the force and the magnitude of the displacement, you know, the magnitude of the displacement vector is the only thing that changes. We can just solve for where this point is along here by you know, taking our 24 inches and then multiplying it out by the original force divided by the larger force that would need to be applied in here. So those ratios stay the same. So in order to end up with a 240-pound vertical force causing the same moment, then we need a 10-inch span here between the origin and the point of application. And again, that's just measured along the length of the lever. So the next question here is asking whether or not the forces that we calculated in B through D are equivalent to the original force. No, no, they're not. So there's a few requirements for a force to be equivalent. They need to have the same magnitude. The magnitudes in all of these are different. They need to have the same line of action. So again, you can, if you're moving a force, you can move it, say, from here to here and not have an issue. But you can't move it to here, and you can't point it in a different direction even if it's passing through the same point. The line of action needs to be the same. And it needs to have the same sense as well. So none of these necessarily just flip directions, but that is a requirement. So no, none of these forces are equivalent.